So, if we're talking about polarity, we talked about how a polar bond was when two atoms don't share electrons equally, and the electrons spend more time in the custody of one atom than the other. So, what you see here is a image of that where a polar bear and a penguin are sharing these electrons of an ice cream cone, the two scoops, and the polar bear, the chlorine, is going to get a lot more of this than the hydrogen, the penguin. And as a result of that, what we have here is this negative, slightly negative chlorine and slightly positive hydrogen, because even though these electrons are being quote unquote shared, they spend more time with the chlorine. Hence, chlorine has a slight more electron density than it would have had without that electron, and hydrogen has a slight decreased electron density than it had when it just had the one electron by itself. So that's a polar bond. A nonpolar bond is when everything is evenly shared, pulled on equally. So this all boils down to this electronegativity scale, which is the numbers that rank how well they are at fighting. So the higher the number, the better they are at fighting. So we're looking at chlorine, which is a 3, and hydrogen, which is a 2.1. So that's a pretty big difference. That's why chlorine gets that slight negative and hydrogen does not. So as a result of that, there's something called an intermolecular force, which is the forces that are holding the molecules together, not so much the atom or I'm sorry, they're holding the molecules to another molecule. So it's not the atoms within the molecule. The hydrogen and the chlorine here are pretty well locked in place, these two here. Um, so this bond and this bond here, those are for real bonds, shared electrons. That's not going anywhere. So we're talking about this force that would hold these two molecules together. And holding the two molecules together because of this force. So we see this here where, so here's a negative chlorine and a negative chlorine, right? So this thing here means slightly negative. That's a delta. So we have this negative chlorine. So that's just a delta, like a lowercase of that Greek symbol. So those are the negative ones. And then the positive ones here, right? So the positive ones. So they attract each other through space or through the liquid or whatever it is. So this positive is attracted to that negative. This positive is attracted to that negative. This negative is attracted to that positive, and there's a stickiness. And the same thing happens here. We have positives and we have negatives, and they can kind of line up and stick to each other. And so that's what we're talking about when we're talking about polar molecules. You need a positive end and a negative end so that within these molecules they can stick to each other. Now the issue with that, well, actually, before I get into that, water is extremely polar. This is something you should know, certainly taking my course, right? You have your negative end where the oxygen is, the positive end where the hydrogens are. And if you look at that further, so here are those electrons being shared, quote unquote, shared, but they spend all their time with oxygen. And as a result of that, what we have here is an exposed proton. So that's a proton that is now exposed because the electron that was shielding it is occupied over there with the oxygen all the time. So this, right, here's the electrons nowhere near where that proton is. So therefore that exposed proton gives you a slight positive. Oops, wrong color. So gives you, right, so you get a slight positive on the hydrogen side and you get a negative on the oxygen side. All right, so that's what you see here. You get this positive sense around the hydrogens and a negative by the oxygens. So to have a polar molecule, you need two things. You need a polar bond. So we're looking for a large electronegativity difference. And then beyond that, what you're looking for is unequal distribution of that charge. So you need to have one end that's negative and one end that's positive. Nonpolar molecules have a couple things. They could have, if there's no polar bond, which means, something like something bonded to itself. So an oxygen double bonded to another oxygen. Well, those oxygens are no different. So these electrons are being shared equally. So there's no charge different, and therefore that would not be polar. So if you don't have a polar bond, you're not going to have a polar molecule. If you have a polar bond, you can still have a nonpolar molecule if there's symmetry in that arrangement. So you see here with carbon dioxide, the oxygens are on either side. So this doesn't really work as a polar molecule like this would. Remember, what we need is the ability to stack. And if you don't have that, which you don't here with this carbon dioxide molecule, then it's not going to work. So let's see that in a little more. So I made a little movie here. Hold on a second. Let's get there. All right. So if you look at this, so if this is so you have your negative end and your positive end. And what you're going to see here is if we bring another molecule, the whole point of it is that the negative and the positive can click like Legos, right? In the same time, the negative and the positive can click just like those Legos, right? It could come from either direction. But if we have a situation like carbon dioxide or something symmetrical, now there is no place, right? This is the bumpy part. This is the bumpy part. While there is a place for the positive to stick, there is no place for the negative to stick. And so that breaks up the ability of this having a polar sense. So basically, you need a plus side and a minus side. So if we go through all these examples, we have a plus side here with a hydrogen, a slightly positive, and you have a slightly negative side on the Cl. Okay, so these hydrogens are all slightly positive, but you have a side. Right? There's a distinct side that they're on, and then that nitrogen is a negative. That's on a distinct side. So you could stack these up. And part of the reason this nitrogen's negative is it has a lone pair right there. Okay, so here with CH3Cl, so it's that chloromethane. You have these positive hydrogens again, right? And it's all directional. You have these slightly positive hydrogens and you have this slightly negative chlorine. So those can stack. Things that are nonpolar, okay, here you have these negative fluorines, but they're surrounding that positive boron. And since they're surrounding the positive boron, nothing can really access that. To get the Legos to stick doesn't quite work. Same thing here. So these have symmetry. You have a sort of a ring of negatives around a center of positive, and nothing can really access that positive center because to get the whole clicking action of the Lego together. Okay, so hopefully that makes some sense. That's what polarity is. Um, if you want to look at that further, like I said, you always just look up PhET polarity. So if you look at, so like here's CH2F2, and if we put on the positive negative side, so you see how we can line this up? So there's a positive side and a negative side, so we can stack the Legos. If we had all fluorines, oh, that's not all fluorines. If we had all fluorines, now that inner area is positive, but nothing can access it because of the symmetry. So if we had just one hydrogen, that's enough to make a positive side and a negative side so they can stack like Legos. So the point here is you want to be able to stack them. If you have a negative and a positive side, that's possible. If you have symmetry, trying to find something else here that's more symmetrical. Well, oxygen just doesn't even have a polar bond, so that's not gonna, there is no charge difference. So that's that. But I guess that's, oh, this one is also the symmetric, right? So that has a positive center and negative ends. So you can't really stack them like Legos. All right, that's all I'm going to talk about.